So the work I present you today is something I did in collaboration with a Swiss company called 3DIAM, which is doing a industrial coating line with digital printing for printed circuit boards. What is a conformal coating? So it's something very useful because think about you drop your mobile phone in the water, and if it's not protected, it will corrode the wires and the parts, and it's broken. And it won't get any damage if it's conformally coated like this with some protective coating. By the way, my mobile phone died this way 2 times in the sea. And yeah, in addition to environmental protection, you can also use the conformal coating to go underneath the parts. That it can be done with vacuum and pressure cycling, so you force the liquids underneath the components, and then you can increase the operational voltage. And since it's environmentally protected, you have also a much higher accuracy of your devices over a long time, since aging is reduced. The current processes to do this is, for instance, dip coating is the main process, but you have some pretty specific design limitations. If you see this, they don't dip the connectors inside. If you want to have connectors on the other side of the PCB, not possible. Or there's other design rules. If you want, for instance, to have one layer not coated here, it's not possible as well, because it has to be either in the conformal coating or it's not coated. So the alternative to this is a selective coating solution. And since it's a really high demand from industry, there's many companies offering this, like 20 different you can find if you just Google this on the internet. The 2 methods that are mainly spread, the most common one is the selective spraying. So you do a liquid film spray on your PCB, and you coat all areas you want with an NC process. So you do numeric control of the orientation and of the position of the nozzle while spraying at a constant rate. And this works quite well. The resolution is quite low, in the millimeter range maybe, and it's very hard to scale up. You would need to have one XYZ system with a spray per PCB to work in parallel. So it's only for small-scale production and prototyping. And that's when 3DIAM came up with the idea of inkjet printing. So there's many different coating materials you can use, depending on the application that you have. You may want to have something that is very tough and hard to remove, or just protecting very well with like waxes against humidity, or something acrylic that can be removed afterwards with the soldering iron if you want to do some fixing on the board afterwards. So in our case, we went for drop-on-demand technology, and this is my timer. So don't mind the phone. And yeah, apart from all good things, like you can really do each PCB differently. You could just get a stack of PCBs and test different designs inline with variable data. You can also not take care too much about the orientation of your parts, but do with machine vision, real-time rotation and translation of the print data to match registration with the printed circuit board. The disadvantage is mainly you have only limited viscosity range, so you can use it for low viscosity conformal coatings. And normal printheads operate at maybe 1 to 5 millimeters row distance. And for a reasonable product from our industrial partner, we needed 15. So what do you face when you printed a certain speed, a certain distance, and a certain part height? So I tried to depict it here. You have an angle of the printhead that you can tilt, could also be 90 degrees, and you have a speed of the substrate. So when the substrate moves in this direction, doesn't matter also if the printhead moves in this direction, then you have a shadowing effect, a shading, because the actual drop flight angle is in this direction. The faster you go, the more this angle will increase, just like the vector you see here. So the drop has a speed that is to the substrate, and the overall speed in relation to the parts on the substrate, and this is then flight angle. Okay, I call it alpha flight. When you consider shading, you cannot print in this area here because no drop in the first pass will land there. You have to do a second pass or a pass orthogonal to this in the Z direction to also print in this area here and maybe also there. So when you have to deal with certain part height, you cannot tilt the print head too much or go with the substrate speed too high, or you will encounter some defects in the coating, especially when these two shading angles from the forward path and the backward path overlap. They must not overlap. For our application, we have 50 millimeter part height, and 2.5 millimeter max shading is a design rule of our industrial partner that makes afterwards a minimum component spacing dependent on the height with an angle of 9.5 degrees. So at 9.5 degrees alpha head, you have to have 0 substrate speed. Good. Other than that, if you think about what you do actually when you print from the top to a 3D shape like this, there's a rectangular grid of your pixels if you don't modify it and increase the density. You take a look from the top. This is a square pixel here, which looks afterwards like this. And that means on this area, if you don't change the number of pixels per square unit, in this range you get one drop here for maybe 100 times the length. In our case, it's a factor like 10 to 15. And if you want to print here, you have no guarantee that the drop will even land on the edge. So that's why for large parts, when you want to do an uniform coating, you have to print at least like 4 passes. You do this one for shading the backward path, which, by the way, can also be done in single pass if you have different printed angles and low speed. And then you print another path here, another path here, and you end up with this area where you have to print square root of 2 more to have the same quantity. Great. So, in the most simple way, you can think about it like this. You print just normally. You have the printed without any tilt, and the drops will go according to the substrate speed with the flight angle on the side. And this now may be much less than what you need, so you need to do multiple passes, and ideally you also delay the passes so that you cover the space in between. So you effectively, what the substrate sees when it is moving into the drops is just a fountain of drops, and it's hitting all drops at the same time, except even if the speed changes. What's the problem also? If you have a lot of speed change due to deceleration on this huge flight distance, then the coating density with a regular pitch will relate directly to the drop speed. If you have a lower drop speed, it means your drops get closer together. And if you have higher drop speed initially, that means if you do the same number of passes here with the same spacing, then you will have less quantity the higher the drop speed is. So to reduce passes with this, you should actually reduce the drop speed, but then you can't reach the throw distance. So this is a contradiction. The only thing that you can do to reduce the number of passes other than drop speed and increasing jetting frequency and throughput is to tilt the angle. But the tilting with an angle, so that you have the you could do 60 degrees, then the sinus of the 60 degrees will be 0.5, and your nozzle pitch and the density you apply per pass is twice. It's the same as rotating the print head. When you print like this. And if you do this, however, you lose, of course, print width. And for a white PCB, it's the same as just taking 2 print heads. Then you have 2 printers in series. It's single pass for the same number of for the same number of nozzles, and it doesn't make a difference whether you move the substrate like this or you just double the number of print heads. Okay. Also, for a limited part height, you can also just flood the parts with sufficient quantity, and you will overfill the top layer, and it will flow down more or less defined over the edges. This does not work if the parts are very high. And yes, that's why we cannot always count on it, but like smaller parts, 5 millimeter height, 8 millimeter height, we could cover quite well just like this. If you use printed tilt, then you have the flight angle, which is here, And you have the same drop speed times divided by the jetting frequency. This is divided, I'm sorry. And you get the density of drops according to your substrate speed. And unless your angle is 90 degrees, you can just apply the same quantity you want at a certain speed. So it means you can control the thickness of your layer directly with a single pass. And yeah, the disadvantage is you have to throw the drops further. When you tilt it by a certain angle, then the overall way until it reaches the bottom is, of course, by the cosine of that angle higher. So, last but not least, as I said before, our maximum tilt angle for the printed is limited according to the shading that we specify for the design of the PCB. Considering the performance, this is quite interesting. Here, if you want to print vertically 50 micron layers with a jetting frequency of 4 kilohertz and drop speed 5 meters per second for 40 picoliter, 5-degree head angle, then you can print with maybe like 1-2 millimeters per second at a single pass operation, because the tilt is very little and you need to apply lots for the height. And if you increase the number of passes where you apply the quantity higher and higher and higher and higher, at some point you reach this point here. The curve is, by the way, the maximum substrate speed you could do for this application when you print on flat. So if you reach this point here, then you have the maximum productivity. That means for this configuration, if you do like 32 passes, you can print everything in 10% of the time, meaning that you have to pass by with the PCB 30 times. But I will show you in the next slide why it's the case. It's quite easy to understand. Also, if you tilt the printhead a little, this is what, like 1 degree. Here we have the printed tilt, and you tilt it more and more and more. Then the ratio gets better, and the total necessary drop speed to have the minimum printing time and substrate speed is reduced. So if we go to like 9 degrees of tilt, we have 9.5 is the maximum. We can do it in single pass with a quite good performance. And you have a substrate speed that is reduced from 0.7 meter per second to 0.05 meter per second, which is approximately the speed that we used in the end. So why is it better to print multiple passes from a performance perspective? Yeah, easy. The printhead is at full load when the pitch here is the same pitch here. And then when you want to coat the same thickness on the bottom as on the side, then and these pitches are the same, you can jet at the same frequency. So the printhead can run at 100% all the time for the coating application. If this one is much higher and you need to do a second pass because of just this height layer, then you have to slow down everything else. You will need to have the same number of passes. Your parts can be anywhere on the PCB, and it's slowing down. So that's why, ideally, if you have no tilt angle, then the sinus of this is 1, and the substrate speed is the drop speed. If you tilt, it's by the sinus of this angle lower. And in our case, for sure, we cannot go with 5 meters per second substrate speed, because the drops will not even land where they should. That's why the limitation is still the shading and the print accuracy. How did our system look like? We have a hot melt feeder from Robotech, Swiss company, a huge filter. Then we have a valve system for distribution and 2 times Galaxy 256 HM printheads. Then we have a degassing vacuum. It's important to have degassing for this. If you turn it off after 1 minute of operation, you lose all nozzles. Then the pressure regulator with negative pressure and purge pressure, a heated PCB for test printing, preheated fan. And here we have, for analysis and for long-term tests, a drop collector and a waste collector with 220 liter. We printed already with these 2 printed like 300 kilogram of wax. And here's also something nice. It's a heated contact-free maintenance. We use our Inkjet Cost platform printer, which is very simple, and just assemble it slightly different to have it meet the requirements of the project. Our substrate temperature we set to 80 degrees, 5 millibar meniscus pressure, and for the test that I show here, it was 1.5 kilohertz. Rito, my colleague from 3D used 4 kilohertz, which is it's like 3 times higher than what the throughput should be. And the wax has a viscosity of 8.5 centipores. We measured the flow curve up to 5,000 shear rate, and it's a Newtonian behavior, totally, like we expected from a wax. And we also got the melting point at 105 degrees centigrade, and the solidification temperature with 90 degree peak. We tested also a couple of charges to check whether this type of wax is sufficiently reproducible from the supplier to be used for industrial application. And it's, this is a very old charge, which was crystallized. And after crystallization, we did the green one, for instance, again, and they really are very, very repeatable in terms of jetting properties. So if you cool the wax lower at like 10 Kelvin per minute, it crystallizes. And it will give you more tension while the wax is solidifying, and can lead to cracks. I come to this later. And at higher cooling rates, so if you let it cool down faster, you reduce the substrate speed, it is amorphous. It has excellent moisture protection and is not the best for shock resistance, but it was an application of our customer. We tried a number of waveforms, single pulse, triple pulse, quad pulse. I gave you all the details here. We did this pulse always smaller because else the first drop would disappear and we cannot catch up. And the last pulse we had to reduce to 130 volts, or else you get another drop. And I could not do a damping pulse here because my print system limits me to only 8 pulses. That is something they can improve. So for the single drop waveform, this is 1 to 6 millimeter flight distance, and this is some time steps. I can't recall what I did, but anyway, this is 10 to 60 millimeter, and it's absolutely like spray. Not even 70% of the drops hit the substrate, and yeah, you can't print like this. The 240 picoliter quad pulse waveform, on the other hand, was already sufficiently stable. This is the significantly larger drop, and we have also acceptable variance in the dot position on the drop watcher for printing. And we printed also some samples with this. This works well. And for the 8 pulse waveform, we got a drop volume of 440 picoliter. And we have less statistical spread on the dot position. It's more stable, of course. And we come to some curves like this. So we start at 7 point something meter per second for the single pulse, 80 picoliter, and we end up at 3 meters per second after the flight distance, and it's not repeatable. And for the 4 pulse waveform, the 8 pulse waveform, they are stable enough, and the least of deceleration with the 440 picoliter waveform was something like less than 1 meter per second deceleration. So we went for the 8 pulse waveform because of the superior deceleration profile, and also we could increase the throughput slightly. When you calculate the 240 by the maximum frequency we could run, we get more efficient in terms of throughput with the 8 pulses. We tested also the repeatability of our prints by printing many test patches. So we print some patch, and then we measure the accuracy, how we can reproducibly print the same patch on the same position. And we come to some mean error of 150 micron for print start and 140 micron for print stop, and like 50 to 70 micron in the cross print direction. And this is definitely sufficient for this application. It's even more accurate than what we expected for the distance. And it's not the end of it. We didn't do perfect calibration for the printhead. So if you do more effort for the waveform tuning, you will be able to improve the accuracy over this throw distance. Regarding our print strategy, so in the end, we decided to go for a multipass bidirectional waveform. For parts less than 8 millimeter, we just go with 4 passes and did no orthogonal printing. And for large parts, we printed first in this direction 4 passes, and then in this direction 4 passes. And we used around the edges overfilling according to part height. So we actually skip lines in the print data, and yeah, it's like 6 to 1. we can do 6 times more than what we need on the substrate bottom than what we need on the height. Conclusion: we have some overfilling here locally, and it flows down a little. It's not really too helpful, but it's sufficient for the application. We also discovered some problems that you also have with spray coating if you don't pay attention. When you print one liquid layer completely, then there are some hydrophobic layers, especially around the edges of the chips. Like here's one. We printed this one from both sides, by the way. And you cannot get rid of it if you print fully liquid. That's why we decided to go for a printing test where we print first a very thin layer, just that solidifies more or less immediately, reduce septal temperature to 80 degrees, and then we print a sealing layer that doesn't fully melt the liquid layer. Looks like this. You see there's some lines with the wax on the PCB parts. This is an 8mm capacitor. There's also some sticky wax on the side of the thing. And afterwards, we overprint this either with the 8 passes XY or with the 4 passes in X. And you see it's somewhat liquefied, but it's not fully liquid. And like this, we really made it to meet the corrosion test requirements, which is necessary for the success of our project. However, if you print it afterwards more than 300 micron, and the cooling rate is unfortunately low like this, because you cannot it will peel off if you cool it with even more and reduce the substrate temperature, then we get drying cracks. But 300 micron is not what we want. We wanted to have something like 70, 100 micron max. And yeah, so as I said, the layer thicknesses of 50 to 300, we tested all in the corrosion test with corrosive gas, and there was no damage to the PCB or the parts on it, so it's a success. And the performance was even superior in contrast to spray coating, because spray coating has the same issue. If you do a fully liquid layer, it will flow off of parts that are hard to wet. So, conclusion. It is a suitable process to use inkjet for conformal PCB coatings. And both waveforms that we tested with 240 or 440 picoliter can cover easily 15 millimeter per hour with a tilt angle of some degrees. But we didn't test higher distances since it was not necessary for our application, but they could be quite feasible. And we didn't go all out with the drop size as well. And our PCBs in the end passed the compliance tests, and yeah, when we had more than 300 micrometer layer thickness, we got some drying cracks. And the coating defects we faced, we could get rid of by printing a seed layer first and not fully printing a liquid layer at once. And I don't think you will easily be able to do this with a single-oriented print process. That's why we had to use multi-directions. So you can do single pass indeed. You take one tilt of the printed like this, a second printed tilts in the opposite direction, a third printed tilts from the side, a fourth printed from the left, then you go in one pass. But if you don't tilt it, it's hard. So thank you for your attention and for coming. And if you have any questions, you can always contact me or Rito. He's actually the guy who did most of the tests. Yeah, do you have any questions?
Yeah, thank you very much, Johannes.